So today, C++ has no reasonable standard abstraction for multidimensional data. This is unfortunate because C++ is increasingly the choice for HPC, machine learning, data science, and many of the interesting compute-heavy problems in these domains have a multidimensional shape. The existing abstractions that we have in the language, like nested C arrays, nested containers like vector, and val array, were not designed for multidimensional programming. They're really incomplete solutions, and they often have performance pitfalls and lead to many anti-patterns. So C++ needs abstractions that allow us to write generic multidimensional code. And by that I mean we want to be able to write code that is storage agnostic, rank agnostic, layout agnostic, iteration pattern agnostic, and composable. So that's why we've introduced Mdspam, a multidimensional span type in C++23. It's very similar to C++20's span type. So Mdspam is non-owning, it's just a handle to some underlying data. It doesn't manage the lifetime of that data. And thus, Mdspans should be cheap to copy. It just contains a pointer and metadata describing the size and the shape of the structure. There are some cases in which it won't actually be as cheap to copy as you might like, because that cheapness to copy will depend upon the type of layout that you're using. And as we'll talk about a little bit later, there are some types of layouts that might have more metadata or metadata that requires dynamic storage. So metadata such as the extent of a dimension can be expressed either at runtime or compile time. And this is important because it allows us to do all sorts of clever metaprogramming, and it enables compile time optimizations. But it's also useful because knowing that information at compile time can, in a lot of cases, enable compiler optimizations such as vectorization, which is going to be one of the key themes of our talk today. So Mdspam parameterizes how a multidimensional index is mapped to a location in the underlying data. And we call this parameter a layout, and it can express any kind of multidimensional structure. There's a few different concrete layouts in the standard library for common use cases, but anyone can define their own layout and plug it into an Mdspam. And likewise, Mdspam parameterizes how it accesses the underlying data. The default here is just to perform a normal C++ pointer dereference with an index. But with a custom accessor, there's a number of other things that you could do. For example, you can have a custom accessor that does bounds checking. You can have a custom accessor that uses some sort of special cache bypassing instruction. You can even have a custom accessor that does something like reads from disk, or that performs a remote memory access. So Mdspam uses these extents objects to express the number of dimensions in a space, the rank, and their length, the extents. So extents objects take a variadic number of integrals as template parameters. For dynamically sized extents, this magic value dynamic extent is used as a template parameter, and the extent is passed to the constructor. Now you might notice that this can get to be like a little bit verbose here if you look at this E1 example. But fortunately, in C++20, we added this feature called class template argument deduction. And when you use it with Mdspam, you usually don't need to spell out the entire verbose instantiation. So this E0 extents object here is constructed using ctad, so the template arguments are inferred from the constructor arguments. There's also this alias dextents for the all dynamic extents case, and that takes a single parameter, which is an integral specifying the rank. And why did we special case this all dynamic extents case? Because we believe that that's one of the more common use cases that people are going to have. So for statically sized extents, the extent itself is passed as a template argument, and no corresponding constructor argument is needed. Now you can mix static and dynamic extents. For example, in this case, we have one static extent and one dynamic extent. So we'll just need to pass one extent, the dynamic one, at runtime. So extents objects and Mdspam support arbitrary rank, So you can have as many dimensions as you want, but the rank is static. So you have to know at compile time how many ranks that you want. So Mdspan itself has 4 template parameters, 2 of which are optional. So the first is just the element type. The second is the extents object, and this has to be a specialization of the extents class template. The third is a layout, and the default is layout right. And we're going to discuss layouts a bit more in a few minutes. So the final parameter is an accessor, which performs element access, and the default one just does a regular C++ pointer dereference. So mdspans of all dynamic extents have a pretty simple syntax. With that class template arguments deduction feature that I told you about, you can construct one without specifying any template parameters. And if you do need to spell the type out, it's still pretty concise if you use that dextents alias. So in this example here, M0 is the ctatted one that doesn't specify its template arguments, and M1 is the equivalent one that uses that helpful dextents alias. So the elements of mdspan are accessed via the indexing operator. And in C++23, we added an extension to the indexing operator, allowing it to take multiple arguments. So previously, if you wrote some sort of multidimensional array abstraction like this in C++, you'd usually use the call operator because the indexing operator can only take a single argument. I can write that myself? Yes, you can. Anybody can write that themselves. So the change was just to make the indexing operator like take a variadic number of arguments and it's overloadable. So anybody can write a variadic indexing operator in C++23. So you can also make mdspans of static or mixed extents. So the simplest way to construct these is by passing an extents object as the second constructor argument. And so the idea here is that you're constructing the extents argument using class template argument deduction. And then you're constructing the mdspan using class template argument deduction. So you don't ever have to spell out the full type of the extents object. So now let's talk a little bit more about layouts. The 2 most common layouts are layout right and layout left. So with layout right, the rightmost extent is contiguous. And so that means that its stride is 1, and its stride increases right to left as the product of extents. So this is the layout that C++ built-in arrays use, and this is also the layout that something like NumPy uses. And it's the default for mdspan. So for example, if we have a 2x2 matrix, the 2 elements on the first row of that matrix will have storage locations 0 and 1. And the elements on the second row will have storage locations 2 and 3. So with layout left, the leftmost extent is contiguous. So that means that its stride is 1. And the strides increased left to right as the product of extents. So this is the layout used by Fortran arrays and by MATLAB. So if we had a 2x2 matrix in layout left, the 2 elements in the first column would have storage location 0 and 1. And the 2 elements in the second column would have storage location 2 and 3. There's also a standard layout stride, that allows you to explicitly specify the strides for each different extent. So all 3 of the concrete layouts in the standard library are just implementations of the layout concept. Generically, a layout is something that just maps a multidimensional index to a storage location. Anyone can define a layout, you just are implementing a concept. They may be non-contiguous, they may map multiple indices to the same location, and they may perform complicated computations, and they may have or refer to state. Now, of course, if they're going to do complicated computations that need to have some state of their own, specifically states that's going to be dynamically allocated, that might start to break some of this model of mdspan being cheap to copy. So the best example of this is if you want to define some sort of sparse layout for mdspan, where you're going to have some data structure that's going to store your non-zero elements. that data structure is probably going to need some dynamic storage. And so if you just hold that storage sort of by value, if it's owned by the layout policy, that's going to work. You can make that work with mdspan, but then those mdspans are going to be expensive to copy around because you'll have to copy that dynamic structure that keeps track of where the non-zero elements are. So it's probably better in that case to make the policy non-owning and to do something like a sort of a shared pointer type model, but that gets to be a little bit hairy. So you can define a layout that will work for any type of multidimensional structure, but it's not always going to be the best and most elegant fit. I suspect that for something like sparse structures, we're going to need some new abstraction. One of the reasons, there's another reason for that, which is that the way that you access elements in mdspan, which is one at a time, doesn't necessarily make sense for something like sparse data. For sparse data, you often want to ask a question like, give me all of the non-zero elements in this row. You want to sort of do batched access. And that's not something that you can do with mdspan today. So parameterizing layout is critical because it allows us to write generic multidimensional algorithms that can be used with any layout. And this is essential to portability because different layouts may be needed on different platforms to deliver on performance. So today we have a major vocabulary problem with multidimensional types in the C++ ecosystem. So suppose I write a function that uses some sort of concrete owning multidimensional type like eigenmatrix. So my users are going to be able to pass an eigenmatrix to this function, but what if they have some other type of matrix, like a boost-ublas matrix, or a PETSI matrix, or a Blaze matrix, or a Cutlass tensor, or a multidimensional array that's been passed from Fortran? And so that's where mdspan comes in. By using it in your interfaces, your code can work with any multidimensional data structure. Because mdspan is just a non-owning handle, you can construct one that refers to an eigenmatrix, to a boost-ublas matrix, to a PETSI matrix, to a Blaze matrix, to a Cutlass tensor, et cetera, et cetera. So for example, let's suppose that we had our own row major matrix class, which this one just is very simple. It does not support static extents, it's all dynamic extents. Now, if we want to make this mdspan compatible, we just add a simple mdspan conversion operator. And this will allow us to pass our matrix class to any interfaces that expect an mdspan. Now, in some more complex cases, we might have to define our own layout type because one of the built-in ones that are in the standard library may not be sufficient. But it's still going to be pretty straightforward for us to make our owning multidimensional data types mdspan compatible. So now let's take a look at some examples of how we can use mdspan. So this is a 3D 7-point stencil inner kernel. Similar to what you'd see in a lot of HPC applications. This is from a proxy application called MiniGhost. And here we have two 3D mdspans that represent the problem state. We use this Cartesian product of iotas trick here. So iota is a C++20 range factory that produces a sequence of integers that are monotonically increasing. So like iota of 1 to n gives you the numbers from 1 to n minus 1. And then Cartesian product takes a bunch of ranges and produces the ordered tuples of the combination of those ranges. So in this case here, we are going to get, V is going to be a range of tuples of 3 elements from 0, 0, 0 to, A extent 0 minus 1, A extent 2 minus 1, A extent 1 minus 1, A extent 2 minus 1. So this is just a simple technique that you can use in C++23 today to create a range to a multidimensional index space. Yes, I see we have a question. Yes, std_v is just my alias for stud::views. Yeah. So using that little Cartesian product of iotas trick, I've built a range that iterates the index space of these two mdspans. And then we use a parallel for each to iterate through that space. And we use the mdspans inside of that for each to do the actual stencil update. So if we want to change the layout, all that we have to do is change the input mdspan. So we just change the data types at the top there. Everything else here remains the same, including the indexing logic in the kernel. So this is an example of a simple parallel matrix transpose. So right here we've got, again, we're using that Cartesian product of iotas, or trick. But inside of the code here, we're using spans directly instead of mdspan. And so the problem here is, well, there's a few problems here. First of all, we've written the indexing logic manually inside of this parallel for loop. And that's pretty error prone. It's pretty easy to make a mistake, especially when you start dealing with something more complex than 2 dimensions. But secondly, if we want to change the layout that we're working with, then we have to go and change the kernel of this code. Now, with mdspan, we don't have to do that. With mdspan, the indexing logic is completely lifted out of this loop. And so now we can change the layout by simply changing the type of mdspan that we use. So mdspan has a powerful slicing interface called CppMDspan. And that takes an mdspan and returns a sliced mdspan. Because mdspan is non-owning and cheap to copy, slicing it is also going to be cheap because you're just creating a new view to the same underlying data. The input mdspan is not going to be modified. So for each extent of the mdspan, you pass a slice specifier to CppMDspan, and there are 3 different kinds of slice specifiers. You can pass a single index to be selected for an extent by passing an integral as a slice specifier. The rank of the returned mdspan is reduced by 1 for each single index slice specifier because you've sort of sliced away that entire dimension. You can also pass a range of contiguous indices to be selected for an extent. And then finally, you can pass full extent, which is this magic value that says select the entire extent. So for example, here we have a 3D mdspan M0, and we make a slice of it by selecting 8 indices for each extent, starting at indices 15, 31, and 7, respectively. So the mdspan that's returned by CppMDspan M1 will have a rank of 3 because we didn't use any single index slice specifiers that would have caused a rank reduction. Each of the extents of M1 will be 8. And the multidimensional indices for M1 will just be like offset from what they would be for M0. So for example, M1 of 0, 0, 0 would be equal to M0, 15, 31, 7. So let's look at another example, this time with rank reduction. So we'll slice M0, selecting index 15 for the first extent, the entire second extent, and index 31 for the third extent. So the mdspan that's going to be produced here, M2, will have rank 1. And the extent of that rank will be 128, the extent of the second dimension of M0. Iterating this 1D slice will be equivalent to accessing M0 with a fixed index for the first and third extent. So CppMDspan is a pretty powerful tool for writing tiled algorithms. So let's go back to that parallel matrix transpose that we looked at earlier. And now we're going to write a tiled version of it. And we'll be working with square tiles with extent t by t. So first, we need a range describing the set of all tiles. And to get that, we're going to use that Cartesian product of iotas trick. It's okay if the tiles at the edges extend beyond the bounds of the matrices, because we're going to handle that inside of our parallel for loop. So then we have our parallel for loop. And this time, we're going to iterate over the tiles, not all of the indices. For each tile, we need to create a new sliced mdspan for A and B using CppMDspan. So first, we need to figure out what the range of indices are that we need to select based on the coordinates of the tile. And this is where we're gonna handle tiles that would go beyond the bounds of the matrices. We will just truncate them to the ends of the matrices if they would go beyond the bounds. So now we're gonna take those tuples and we're gonna pass them to sub-mdspan, and that's gonna produce the local mdspans for this tile. So next, we need a range of multidimensional indices within the tile. Again, we'll use the Cartesian product of iota trick. So finally, we use a C++ ranged-based for loop to iterate over the indices of the tile and perform the transpose with the local mdspan slices that we've made. And with that, we're done. So this was sort of the final version of the parallel matrix transpose that I showed you yesterday. And this is pretty good, but let me just get a show of hands. Who thinks that this is attractive code? No, I'm not. Now, I definitely think that it's hard to argue that compared with how you do it today, this is definitely better than the status quo of writing it manually. But is this the final form that we want? No. This is too much line noise, and this Cartesian product of iota thing, that's a lot. That is a lot. And this whole thing where we're creating these local mdspan slices, yeah, this is a lot here. For somebody like me, this is maybe exciting, but I think we can do better. And we're gonna get to that in the back half of this talk. But first I want to talk a little bit about algorithms in the standard library. So C++ has a set of standard algorithms today, things like for loop abstractions, filters, sorts, searches, rotations, reductions, and scans, etc. But they're all focused on one-dimensional data, and they're all parameterized with ranges and iterators. We only have a very limited set of numerical algorithms, such as reductions and scans. And that's why the C++ committee is looking at standardizing new classes of algorithms, specifically multidimensional algorithms. And the first of those that we're looking at is linear algebra algorithms. Now, we don't want to reinvent numerical linear algebra. We're certainly not qualified to do that on the C++ committee. What we want to do is standardize existing practice. And the existing practice for linear algebra is BLAS, the basic linear algebra subprograms. So we want to standardize a modern C++ interface that can be implemented under the hood by existing BLAS libraries. Now, most existing BLAS libraries today have a very low-level C interface, and typically they have these interfaces where they take dozens of different parameters, and a lot of them are these Boolean or integer parameters, and it can be a little bit hard to understand what exactly is going on. So the existing one-dimensional C++ algorithms that we have in C++ parameterize data with iterators, and in C++20 ranges. Now, for our linear algebra interfaces, we want to parameterize them instead with mdspans. And we use these mdspam parameters to simplify these BLAS interfaces. We can express things that appear as distinct parameters in traditional C-style BLAS interfaces as part of the mdspam parameters. So for example, instead of having distinct scaling parameters on matrix vector product, we can have a scaled operation that takes a scaling factor and an mdspan and returns a new mdspan that will apply the scaling factor to the elements of the mdspan upon access. And this is done lazily, sort of in the way that a lot of range views are applied lazily. So C++ standard library implementations can see through this abstraction and extract the scaling factor and feed it into the lower level BLAS libraries. But this gives us a much nicer and more elegant and composable interface at the C++ layer. So another example of this is Transposed, which returns a transposed version of the supplied mdspan. And this allows us to, instead of having these interfaces take a special flag that says transpose this matrix inside of the operation, we can instead have that completely lifted out of these algorithms and just have it be this separate lazy thing that you can do to an mdspan. Yeah, Tony, you got a question?
Tell your translator, or your whatever, not translator, how to spell BLAS.
BLAS is spelled B-L-A-S for the simultaneous translator. So as with today's C++ algorithms, we're planning to have serial and fork-joined parallel overloads of linear algebra algorithms. So in this example, where we solve a system via upper triangular Cholesky factorization, we'd really want to chain the two operations together and launch them asynchronously. So in the future, we imagine that we'll have asynchronous sender adapter forms of these algorithms that will allow you to do just that. And if you want to learn more about that, you should watch the talk that I gave yesterday, which a video will be online, and I've also given it a few times. There are plenty of videos of it. Okay, so I've talked a lot about all the great parts of Mdspam, but there's one sort of glaring omission. Mdspam does not provide ranges or iterators that enumerate its elements. This seems like a pretty glaring omission for a C++ container-like abstraction. So why not? Well, performance. It ultimately came down to performance. You can implement a multidimensional iterator in C++, but it will probably lead to poor code gen. It will either inhibit vectorization or it will involve a bunch of unnecessary and expensive indexing operations. And so because we didn't have an efficient way to implement it, we decided that we were just not going to give you the useful and productive thing. Was this the right choice? I think that's debatable. I think within the goals of C++, it would have been a big mistake for Mdspam to have iterators as we conceive of iterators today, given the limitations of current compiler technology, because nobody would be able to use multidimensional iterators to Mdspam in production code where they care about performance at all. But it's a pretty big usability limitation. I think a lot of people, when they pick up Mdspam, they'll try to do something like a std reduce on them or a std for each, and they'll be like, what? Why doesn't this have begin and end? So why do we want ranges and iterators for something like Mdspam or vector or map? So what makes C++ ranges and iterators so enduring? I think there's a few different things. First of all, there's parameterization. So the iterator and range idioms allow us to lift iteration out of an algorithm, allowing users to customize how iteration is performed. There's also composability. Ranges can be composed together to build more complex patterns from a core set of primitives. So ultimately, ranges and iterators enable us to write generic code. So for example, on the left here, I've got some function that takes a range and it iterates over that range. Now, that function doesn't care about the particular technique that I've used to iterate this thing. So it could just be iterating over the elements of a vector. But I could also have it iterate over that vector in reverse by using something like the reverse range adapter. Or it could iterate through every other element of the vector. Or it could iterate through every other element of the vector or in reverse. Or it could just iterate through the indices of the vector. And all these things are possible because we've lifted iteration out of the algorithm itself. The algorithm does not care how we've done the iteration, as long as we've done it in a way that satisfies the range concept. So as I said at the start of this talk, we want to enable generic multidimensional programming in C++. And so it's natural that we'd want the same idioms that enable generic one-dimensional sequence programming, ranges and iterators. But do they really make sense for multidimensional C++ programming? So let's talk a little bit more about iteration patterns. We don't often think about them when we're iterating in one dimension. So we often think of one-dimensional containers like std vector as having a natural iteration order. You start at the first and you end at the last. And that's what you'll get if you call begin and end on a std vector. But there are other ways to iterate a vector, such as in reverse. And this one's common enough that we do provide standard interfaces for this, like rbegin and rend. But there's other ways to iterate through one-dimensional data. For example, maybe we start at some point and we visit the elements in order of their closeness to this point. Now, in multiple dimensions, we don't have such a natural choice of default iteration pattern. There's no, natural forward. So we might want to iterate in row major order. And it's important to note that the order that we iterate is, in fact, independent of the underlying data storage. So we might have something that is in layout left, but we might want to iterate through it in row major or right order. We might want to iterate through it in column major or left order too. Or maybe we want to do something that's locality-centric, like a Morton order or a tiled pattern. Just as with one dimension, there's many different patterns. But unlike with one dimension, it's less clear that there's a natural default for how you'd want to iterate for any given multidimensional structure, and even for any given multidimensional layout. So a range is just one way to iterate through a sequence. There might be other ways to iterate through that sequence. Those would be different ranges. Now, I often get asked, what iteration order would we use for Mdspam ranges and iterators if we had them? And I think that that's not a well-formed question, because there is no one iteration order. Just like with one-dimensional sequences, you would have multiple different ways of constructing iterators to that sequence that would represent different orders. So the iteration of multidimensional spaces breaks down into two different categories, I think, index-wise and element-wise. So for index-wise, we are going to iterate through the positions in multidimensional space. And often when we're doing index-wise iteration, we're going to be accessing multiple elements or multiple locations within a single iteration. So something like a stencil. So for example, matrix multiplication or matrix transpose, or summing the rows or columns of a matrix, or stencils. Now, in element-wise, we iterate through the elements themselves, and the position in multidimensional space doesn't matter to us. So for example, if we're doing something like multiplying or adding a scalar to every element of a multidimensional data structure, or if we're going to count the non-zeros in a multidimensional data structure, or in fact do any type of commutative reduction. Multidimensional structures have two different position spaces. There's the multidimensional index space, which is logical, and there's the linear storage location space, which is physical. Mapping from multidimensional indices to linear storage locations is typically relatively fast, but it's going to lose information. Now, this is the type of mapping that Mdspam layouts do. They map from multidimensional index to a linear storage location. But going from storage locations to multidimensional indices is usually slow, because information must be reconstructed because it was lost mapping from the multidimensional index space to the linear storage space. And that reconstruction almost always has a non-trivial cost on mainstream processors. Now, the problem is that C++ iterators and their operations are in this linear storage location space. So if you have an iterator that stores a multidimensional index, implementing iterator operations may be unnatural and will often be slow. For example, adding a storage offset, which is in that linear storage location space, to a multidimensional index usually involves control flow for doing your bounds checking. If you have an iterator that stores a storage location, then the iterator operations will be fast, but getting the multidimensional index from it will be slow because you'll have to reconstruct it. So maybe C++ multidimensional iterators aren't actually such a good idea. Now let's find out. We're going to take a look at some different implementation approaches and see what code gen they lead to. So this is sort of the simplest multidimensional iteration, which is a C-style nested for loop here. Now, I'm just showing you sort of the simplified version of this code, but in my actual little benchmarking library for this, there's a whole bunch of nonsense around this, like all of these compiler hints to tell the compiler, hey, like none of these pointers alias, and make some assumptions about the bounds of these loops, like assume that m and n are divisible by 64, and a bunch of other things, essentially to encourage the compiler to give me not necessarily better code gen, but more concise code gen so that it's easier to understand what's going on. We'll talk a little bit in a slide or two about why that is important. So the assembly that we get from this, if we use Clang and are targeting AVX512, will look something like this. And this is a pretty quality vectorized loop. So we've got, you don't need to like read all these specific assembly instructions, you just need to sort of understand the structure of what's going on here. So we've got some setup code at the start, then we've got the loop body of the outer loop, and that outer loop is gonna be scalar. And then we've got two inner loops. We've got what I call a primary inner loop, which is sort of vectorized at a very wide width. So it's unrolled to do 16 512-bit operations, so like that's a lot. And then we have a remainder loop that is at a width of just 4 512-bit operations. And then there's some cleanup code sort of at the end before the function returns. So modern vectorizing compilers for languages like C and C++ are pretty clever. They typically, when looking at vectorizing a loop, will break the loop down into, will generate 3 different kinds of loops for that loop. First, if needed, they will generate a peel loop. And a peel loop is a scalar loop that will attempt to align the inputs and dispatch to a better loop. And what I mean by that is if the compiler can't prove that the pointers that are being used in the loop are aligned, then it'll say, you know what, I'm just gonna generate a loop that will like do some iterations at runtime, and then like after each iteration it'll check like, hey, like, are we aligned now? And if we are aligned, then we can go and dispatch to a better loop, specifically a vectorized loop. Then we have our primary loops. And the primary loop is going to be, your vectorized loop that will assume certain alignments and a certain number of items remaining. And then you'll have some number of remainder loops. And remainder loops will either be scalar or vectorized, and they may make certain assumptions about alignment and the number of items remaining. So the idea here is like you have this peel loop and like it sort of gets you like set up to go into your primary loop, and then you do your primary loop for some period of time, and your primary loop might be unrolled and might handle like a large chunk of elements, but then like at some point the primary loop's like, there aren't enough elements for me to do another iteration. And so then you drop down to some remainder loops, and you might drop down to like just a remainder loop that's still vectorized but still pretty wide. And then maybe in the very end you drop down to just like some scalar remainder loop to finish things off. Now, the reason that compilers do all of this, generate a bunch of different loops for your for loops when you're trying to vectorize them, is because if they didn't do all of this dispatching and runtime checking, then they would have to give up on vectorizing a lot of loops. Because in C++, pointers might alias, and in C++, you might have pointers that are not, like where you don't know that they're sufficiently aligned to be able to use very wide vector operations. And so for a long time, compilers did just sort of give up, but then compilers got smarter and they were like, you know what, we can just like do a few runtime checks and like it won't be that expensive, and then we can like dispatch to the good loops. Okay, so enough about what modern compiler-generated vectorized loops look like. Let's look at some more code examples. So I showed you this Cartesian product of iotas trick a few times earlier. And this is a pretty clever, it's a nice way to write a multidimensional index-based loop just using C++20 ranges, but like, how is the performance of the code? So the code gen that we get from doing something like this looks like this. Now this is actually less assembly than the last slide, so you might think of this as better, but this is not actually vectorized at all. And so if you go and look at the compiler's sort of optimization diagnostics, it'll tell you a few things. So first of all, the compiler will say, well, I didn't vectorize this loop because I couldn't figure out the loop bounds. I couldn't figure out like, when this thing was gonna end. Which is like understandable because that's a non-trivial question, because that's sort of buried in this ranges structure. And it's not just like a trivial answer because there's this nested multidimensional structure there. And so that is at least one of the reasons why it was like, yeah, I can't even try. Now, if you try with some other compilers that are like not Clang, like the Intel compiler will tell you like, whoa, there's like some control flow here that like I don't understand, like within this loop. And now what is that control flow? Now that control flow is sort of the embedded inner loop that is embedded inside of this outer Cartesian product loop. Basically, the compiler looks at this loop and it's unable to understand that you've hidden a for loop inside of another for loop. We'll see that a little bit better in the next example, which is this sort of handwritten index-based 2D iterator. So in this iterator here, we're going to write an index-based iterator that stores multidimensional locations. And we'll just assume that it's column major just to make it nice and simple. And so the sort of interesting part of this iterator is the index operator. So this iterator stores something in the multidimensional index space, which means that its indexing, its increment operator, its C++ iterator operations are going to be a little bit tricky. So you've noticed that I've put some comments here, which will be important in a minute. So let's look at like what this actually does. So first thing we're going to do is we're going to go and increment the index for the innermost loop. And then we're going to check whether we've reached the end of that innermost loop. And if we have, then we want to do an outer loop increment. And then we want to reset the inner loop index to its initial value. And then we want to return the iterator itself. Now, if we look at this operator ++, we can see that all three parts of the inner loop are inside of here. But when the compiler looks at this, the compiler does not understand that we've embedded a for loop inside of this iterator. What the compiler sees is some control flow that it doesn't understand. Now, compilers like to be able to understand loops in some canonical loop form and then lower them down to that loop form and then do analysis based on that canonical loop form. And if they can't lower something down to a canonical loop form, it's just gonna look like weird control flow to them. And control flow is something that is notoriously tricky to vectorize. So let's look at the performance of this code. So this is pretty nice. We can use it just in a range-based for loop. We can use structured bindings to destructure these. But the code that we're going to get, just like with Cartesian product of iotas, is not going to be vectorized. And if you look at what the compiler complains about here in its optimization report, it primarily complains about there's this control flow that I don't know what this is, and I just can't vectorize this. I surrender. Okay, let's look at another approach. So in this approach, we're going to, instead of storing multidimensional index locations, we're going to store the linear storage space location. So just where the element is in the underlying backend storage. So this means that our increment operator will be very simple. We just increment that storage location. But if we want to reconstruct the multidimensional index, we have to do some expensive operations. Specifically, we have to do a modulo and an integer division. So let's take a look at the codegen that we get here. Again, fairly simple and C++ usage here, but the codegen is not great. There's a lot of things that are happening here. So let's look at this in a little bit more detail. Now, what's actually going on here? You don't need to understand a lot about assembly to sort of intuit what's happening here. I'll show you. So we see some integer division operations. And there's actually a bunch of them here. And then we see some vectorized operations. That's good, right? We like vectorized operations, like multiplications. But let's go back a minute and take a look at the loop that we're actually doing. So what is this loop really doing? It's a memset loop, right? Memset should not be doing any real work. And that's why I choose memset for this example. Because the idea here is to show you the overhead of the abstractions. And memset should be very, you're just setting something to 0. That's very straightforward. There's no compute there. It's just some data movement. So then what is all of this compute that's happening? Well, this is all the indexing calculations. This is all the cost of reconstructing the multidimensional index, of doing that, that modulo and that division. And so again, you know, the memset loop, like this is like the most minimal loop that you can have. And so like this is going into using this type of iterator, like this is like your default baseline overhead for this. This is pretty not great. All right, let's look at another example here. So a few years ago I had a clever idea, and clever in both the good and bad sense of the word, which is, well, if the problem is that, you know, we want to have this collapsed iterator, you know, C++ iterator style construct that sort of collapses an inner loop into some multidimensional iterator, but we want the compiler to be able to understand that there's an inner loop embedded in there. Maybe we can use coroutines for this. Because there's a bunch of optimization machinery around coroutines, and so if you write some sort of multidimensional index generator like this, and you use it in some range-based for loop, you know, sort of in theory, what the compiler should essentially do is should take these nested for loops here, and after all the coroutines optimizations, it should just sort of drop those for loops into the place where you use the generator. And then that should get you to good code gen. So let's take a look at what happens. So we can, again, use it in sort of the way that we want, which is that we don't have to write a nested for loop. We can just write a C++ range-based for loop, and this can be rank agnostic and layout agnostic. So what code gen do we get? Well, we get this, and this is actually not bad. This is vectorized. You can see here we have a vectorized move operation. Now, this is not vectorized in the way that the C-style for loop was vectorized. In particular, it's not doing a bunch of unrolling and generation of multiple loops. And the reason for that is because this technique still confuses the compiler a little bit. Now, arguably, this may be better code than the other example. If you run the other example through different compilers, some of the compilers are like, it doesn't actually make sense to do all the unrolling here. But it is a little troubling that, that this technique did confuse the compiler and did not lead to the same code gen that you would get writing the raw C-style loop. The other problem with this is that this relies upon the compiler's coroutine optimizations. And I think it's never great to have a functional feature which is like reliant upon a certain series of compiler optimizations like this. In particular, sort of when it's relying on compiler optimizations that were not really designed for this purpose. So this approach, I think, does have promise, and it does work. Now, one of the limitations of it is that if you try to write this generate indices in a rank agnostic way, where you instead of having like two manual like raw for loops there, you want to write something that's like, you know, generic and rank agnostic, you end up in a situation where what you really want is to be doing nested generators, where you you have this returning an index nd generator, and then the way that it builds up like a multidimensional generator is it like returns a nested generator of a nested generator of a nested generator. The problem is that nested generator technique tends to turn off a bunch of the coroutine optimizations, and then you don't get the nice vectorized code. So this technique only really works if you're willing to hand roll out these generate indices functions up to whatever already you want. Now, it's possible that we can improve upon that in the future. Okay, so how can we solve this problem? So there's a few different things that we could do. First of all, we could try to teach compilers to recognize the sort of non-loop control flow patterns that we would use inside of these multidimensional iterator approaches, to recognize them and to be able to turn them into loops. So basically, we could try to teach compilers like, hey, this like multidimensional iterator, like it's actually got a for loop like embedded inside of there. Now that is not an easy task. It's probably a few PhDs, theses worth of compiler research. We could also probably develop some compiler built-ins that multidimensional iterator authors could use to describe the inner loop, to tell the compiler like, hey, like this control flow, this is actually like an inner loop like condition, and this is an inner loop init expression, etc. And then that would be a little bit easier. Then the compiler would be able to be like, oh yeah, like I know what that is. Like now I can transform this into like the inner loop form that I know. So we could provide element-wise ranges and iterators that don't expose the multidimensional position. So this has got some use cases, like if you're doing something like adding a scalar to every element or multiplying a scalar by every element, you want to do something element-wise, and you don't really care about the multidimensional position, and then you don't have any performance problems. And finally, we could not use ranges or iterators for multidimensional data structures. Maybe, in fact, we could build some new constructs instead. So this is what a range-based for statement looks like in C++. You know, it takes some range declaration and then some range element declaration and some initializer, and it sort of expands out to this code here. And one of the key things I want you to see here is this sort of range protocol that the compiler understands, in particular the begin and end. The compiler knows like, hey, if this thing has a begin and an end, then I take this nice range-based for syntax and I unroll it to this code here. This slide may be out of order. So this is essentially what the range protocol that the compiler understands looks like. You know, it's begin and end. Now, what if we were to come up with some new protocol that the compiler could understand for multidimensional spaces? Perhaps something like this. So we've got an mdbegin here, which takes a few different things. First of all, it's going to take an explicit template parameter, which is the rank that we are at. And then it's going to take this space object, which is some concept similar to a range. And then it's going to take this, this variadic tuple that I'm going to call outer, which is sort of information that's going to be passed from the outer loops. We'll see how that's used in a minute. And mdEnd takes the same set of things. And then we have an mdRank, which is just going to be some compile time or some template variable that will tell me like, hey, what is the rank of this space? All right, so let's look at how we might use this. So imagine that we had some sort of space-based for statement, where just like with a range-based for, you've got some iteration, you know, initializer, and then you've got some for space that you pass, some space that you pass in. And so what this is going to expand to is this sort of nested multidimensional loop. And in the outermost loop, you're going to call mdbegin on the last rank. And you're just going to call it on the space. And that second argument, it's not going to exist yet. And so then that's going to give us back k, which is going to be just like the outermost iteration value. And so then in the next innermost loop, we're going to call mdbegin again on the next rank, the next innermost rank. And importantly, we're going to pass the result of dereferencing the iterator from that outermost loop. And we'll always do that at subsequent stages. We'll always dereference the previous outermost loop's iterator when we call mdbegin and mdEnd. And what that gives us is this way to sort of incrementally build up a multi-dimensional index in this traditional nested for loop structure that the compiler will be able to understand. So we can do a lot of the things with this that we would be able to do with ranges and iterators. Specifically, we can do things like composition. So imagine that mdspan had a method indices that returned to us one of these space things. We could imagine that these space things could be pipeable and that we could do something like, you know, a filter on one of these things that would filter so that we just get elements that are on the diagonal. We could also imagine being able to do range adapters that are applied just to one level of the loop. So this filter here would be applied to sort of the innermost loop. But maybe we want to do something, some sort of filtering or transformation in one of the outer loops, one of the more outer loops. And so we have this little helper called onExtent, which says, hey, take this range adapter and apply it at this level in the nested loop hierarchy. And you could, compose together multiple of these onExtent range adapters together and allow you to do something like say, I want to select just the indices where J and K are 0. And we could also do something like selecting just the interior points here. And here we're going to use the stood views drop and stood views take. And we're going to do one on each one of the extents to just select the interior points of a region. So this doesn't stop us from also providing traditional ranges and iterators for element-wise access. Now, those traditional iterators would not expose multidimensional indices, but this would mean that you could take an Mdspam and you could feed it into something like a stood reduce. You just would not be able to get a multidimensional index out from one of those iterators because it would be slow. If you wanted to do something that's index-based, you'd use indices. So let's revisit some of the earlier examples and see if we can improve them with this new space paradigm. So here's our matrix transpose example from before. So if we had this space paradigm, then this would look like this. Now I'm fairly happy with that last slide, but I think that this is going to be a little bit better. Now there's a few different things that I'm using in this example that we don't have. So we don't have parallel algorithm overloads that accept ranges and spaces directly instead of iterator pairs, but that's coming. And we don't have this indices method, which would return one of these space protocol things. And we don't have a language extension to allow us to destructure tuples in parameters, which would be really nice because then we could do the little destructure syntax inside of the lambda. But I'm starting to like this code. This is starting to look like the code that I would ideally want to write. And going a step further, of course, I would want an asynchronous version of this that parameterizes where it actually runs. And now this is really starting to get exciting for me because this is code now that I can take and I can run it on any hardware that I want in parallel, and it's fairly concise and easy to understand. So let's go and revisit this example of the 3D stencil. So we can get rid of that Cartesian product of iota thing. We can just write this. All right, this is better. Starting to like this one. Now we could also do something like this if we wanted to apply the stencil just to the interior points. See, this is composition, right? That's one of the key things that we want out of something like ranges or iterators or this new space idiom. That I can go from applying, the same code here just by changing the type of space that I pass in. I can change what I'm iterating. And here is a version that's not parallel, that's just using the space-based for loop. Because I work at NVIDIA, I just care about the parallel version. But I think this shows you sort of how elegant this is and how well this approach, I think, would fit in to C++. Okay, so let's go back to that tiled matrix transpose that we saw earlier. So again, this is better than the status quo. I don't think that this is how I want people to write code in an ideal world. So let's see if we can improve upon it. So we can get rid of that Cartesian product of iota stuff. And in fact, we can get rid of doing sub-mdspan at all. We just, on the outer, we get the index space from one of the mdspans. And we just say we want to stride through it. Because we want to iterate through the tiles. And stride will take care of that whole out of bounds thing for us, for the most part. Oh, no, actually, we still need to do the correction there. And then inside of the for loop here, we don't need to do any of that Cartesian product of iota thing. We just construct an MD space, which here is just going to be some concrete, sort of iota-like thing, but for multidimensional spaces, that will iterate through all of these points that we've described here. And so if we get rid of the parallel for loop, we just replace it with the space-based for loop, we can make it even more concise. And so this is how you would write a tiled matrix transpose using this space idiom. So I think that this is a better approach than trying to force an iterator abstraction on Mdspam. Now, it does mean that we would need some number of new abstractions. So for example, doing a std for each on Mdspam might not necessarily do what you want without modifying for each to understand like this space protocol. Now we can modify for each to understand the space protocol, but this means that like in all of your code, you would need to go and teach it to be space protocol aware. So there would be some amount of struggle there in that we would need to go and roll out new overloads in everybody's code bases that are space aware, but this would allow us to get to the performance that we want. And this code here, all of these codes that use the space protocol, they generate the same assembly that you'd get if you wrote the raw C for loops. All right, I think I'm just about out of time, so I will take some questions if anybody's got questions.
Yeah, so you showed, a language extension that would allow structured binding in function parameters.
Yeah.
And as far as I can remember, there was a proposal for that was refused. Do you think the opinion of the committee would change to allow this in the future?
I think the committee is wrong on that count. Will I convince the committee that they're wrong?
It's from memory.
I don't know.
Might be
maybe.
imagining something.
Like I think that having to do this, like this little nonsense right here, like that's pretty bad, and like that's just syntax. I would very much like to revise that proposal. I'm going to continue putting like the way I want to write it in slides until this is the way that I can write it. Yeah, like I don't know. I don't remember the exact details of why the committee said no to it. But I think that this is just a huge usability enhancement. It's not just for this multidimensional stuff. For senders and receivers, being able to do this destructuring in the lambda is like really key because senders and receivers do this thing where they like send multiple values. Like anytime you're working with tuples, like this is huge. And like just having to do this like destructuring where it's like the first line of your lambda, it just adds so much noise and so much pain. I think we have to fix this problem.
Thank you very much.
I'm just not familiar enough with Mdspam. Can you compare Mdspans with each other?
What do you hope, what is the outcome that you desire from comparing Mdspans of each other? That
they represent, that they're pointing to something, the two ranges of values that are the same, two spans that are the same. A deep comparison.
Yeah, I don't believe it's a deep comparison. Daisy, it's not deep, right? I believe it's like span and it's shallow.
It's shallow, and the reason it's shallow is because it's a reference type, and so if you do a comparison of std spans, like any other reference type in the standard, they also compare pointers.
Yeah.
So it is a pointer comparison, so there's equality and non-equality of the...
I will make a bold claim that if you want deep comparison of any range or space, you should be using std equals, not the like equals operator.
Yeah, reference types in the standard in general don't,
Yeah.
or pointer-y types don't do deep comparison.
Yeah, so the reason that I say you should be using the algorithm std equals is because in a generic context, you are not necessarily going to know.
So how would you use the algorithm for equal on an Mdspan if there's no iterators?
But if we had element-wise iterators, then you could use std equals.
That's what I meant.
Yeah.
You can, for contiguous ones, you can get the span out of it, and then you can iterate over that.
Yeah, you can't do it today, but but in Bryce's future vision world, you can.
Did we get that out? Did we remove that?
I don't know. That's,
I think there's an operator span that you can use.
I believe there is.
And then for taking a slice, and you had a tuple there.
Yeah.
Can you put the tuple so the second one is greater than the first one, and it's a reverse slice?
No. That does not work. That's going to be,
Well, so what will it do?
It was discussed.
Yeah.
Will it just compile and, hey, everything's fine, or will it throw an exception?
I don't know what the failure mode's on that's going to be. Probably not great. I suspect it's UB if you do an out of bounds slice. Yeah, it's probably UB if you do an out of bounds slice. So don't do that.
Okay.
Tony?
Now I need to know, standard span doesn't have comparison, does it?
I do think we took a comparison out of Mdspan for just this reason. I don't think we took it out of Mdspam. I could be wrong.
We did whatever span.
So I suspect we did whatever span does. So it's probably consistent with span, so you probably can't compare them. But like the short answer here is like you shouldn't be comparing them. It's probably not what you want. You probably want just like std equals. If you really want to just check that they're like pointing to the same thing, do like dot data equals. Like you should write what you mean. I think that there's no context in which span equals other span or mdspan equals other span is not going to be ambiguous to somebody. Std equals is going to be pretty clear because it's clear that that's an algorithm that's doing like element-wise. And if you want to just make sure that they are referring to the same thing, doing like data like equals and then checking the metadata, which is actually a little bit trickier for mdspan, is probably the way to go. Other questions?
In MD array, the value type version of this, that's hopefully coming at some point, will likely have element-wise comparison in that respect, just like other value types in the standard. So the goal is to just be consistent with the rest of the standard so that scientific computing people can do standard-like things with scientific computing software.
Any other questions? Nope. Thank you all.